Swayamprabha. Digital India. Educated India.
In our previous lecture, we were discussing about the equation of motion for a fluid flow without any specific emphasis on what type of fluid it is to begin with, and then we gave some particular attention to some special type of fluid which is called as Newtonian fluid. That is a fluid that will obey the Newton's law of viscosity. So, we found that for a Newtonian fluid, if you look here, you will see that for a Newtonian fluid we have come up to this relationship, that the deviatoric component of the stress tensor tau ij deviatoric is nothing but Cij KL EKL. So, the Cij KL is a fourth order tensor that maps a second order tensor onto a second order tensor. So, there are 81 components, and symmetry will reduce the number of independent components further, but those are still too many in number to characterize a fluid in a practical manner. So, we will go for some special considerations which deal with homogeneous and isotropic fluids. So, to get further into this issue, let us go to the board and try to understand that Cij KL, this is a fourth order tensor. Now, let us say that if it is isotropic, it is possible to convert this into an isotropic scalar. To convert this into an isotropic scalar, we can take aid of some vectors. Why we can take aid of some vectors is because, see, to make it a scalar, we should make it index free. This has now 4 indices. To make it a scalar, we should make it index free. So, to make it index free, we should have another repeated index I, another repeated index j, another repeated index k, and another repeated index L. Okay. So, each index can be donated by one vector, because a vector can be specified by one index. So, if you have a vector A that can, so to say, donate the index I, a vector B that can donate the index j, a vector C that can donate the index k, and a vector D that can donate the index L. So, if you have Cij KL into Ai Bj Ck dl, then this I is repeated, j is repeated, k is repeated, and L is repeated. That means there is an invisible summation of this over this, and it becomes a scalar, right, because it becomes index free. Now, what makes it an isotropic scalar? If it is an isotropic scalar, then it should not be dependent on the absolute orientation of the vectors. That means, if you have the vector A and B, let us say this is vector A, this is vector B. Now, if you rotate this system so that the vector A comes to this new location and vector B comes to this new location, then the scalar should not depend on this rotation. That means it would be same for the original orientation of AB and final orientation of AB, there should not be any change. So, that what it means is that the result should depend on only the angle between A and B, their relative orientation, but not their absolute orientation, because during rotation the angle is preserved, right, the angle between A and B, that is preserved after it is rotated. So this is like reminiscent of rotation of coordinate axis. So if you have two axes, say A and B are like, say for example x and y, angle between them is 90 degree. So if you rotate them, still the angle between the new x and new y is 90 degree, right, that does not change. So what we can say is that it will depend on the angle between A and B, but not the absolute orientation of A and B, and angle between A and B may be specified by the dot product of A and B. So this can be written as, if S is an isotropic scalar, isotropic scalar, then this becomes a function of the dot product of vectors taken two at a time. So A dot B can be written as AI BI, right, because A dot B means what, the multiplication of one element of the vector A with the corresponding element of the vector B and summing it up for I equal to 1 to 3. So this is A dot B actually. So if we have A considered with B, then we have C considered with D, this multiplied by a factor plus So how many such combinations are there? You can combine A with B, then C gets combined with D, you can combine A with C, then B gets combined with D, and you can combine A with C and B gets you can combine A with D and then B gets combined with C. So there are three such possible combinations. So each combination can be associated with a scalar, let us say this is alpha, this is beta, this is gamma, these are just coefficients. So see, just by considering isotropy we can bring down the number of coefficients necessary from 81 to 3. Okay. Now the thing is, the next step is a little bit of algebraic manipulation. Here in the left hand side we have, here you see you have Bj, but here you have Bi. To make left hand side comparable with the right hand side, we can use the Kronecker delta, so that you can write Bi is equal to Bj into delta Ij. Why? Because delta Ij is equal to 1 only when j equal to I, then this j becomes I, so it becomes Bi. So this is a trick by which you can switch indices. So if you want to switch from I to j, j to I like that, you can use this Kronecker delta. So now so in place of Bi we can write Bj delta Ij. So Ai Bj Ck in place of dl dk, if you write dl, then what would be the next thing? Delta kl. Next term ai bj, then ci, if you want to make it ck, delta ik, right, and dj dl delta jl. Okay. Similarly, for the last term ai bj, then cj to be converted to ck, so ck delta jk, and di to be converted to dl, so dl delta il. So you can see the right hand side also, all the terms are of the form something into ai bj ck dl. Okay. So you can write Cijkl is equal to what? Cijkl is equal to alpha delta ij delta kl plus beta delta ik delta jl plus gamma delta il delta jk. Now let us look into the conditions under which we have derived it. We have used the isotropy. What does the homogeneity come into the picture? The homogeneity is implicit, that means this alpha beta gamma are position independent, that is the homogeneity. I mean these are constants not depending on position. Now these are three constants. We can bring the number of constants further down by noting that you have tau ij is equal to tau ji, right. That means Cijkl is equal to Cjikl, right, because tau ij is equal to tau ij is what? Cijkl ekl, tau ji is Cjikl ekl, therefore Cijkl and Cjikl must be the same. So that means in this equation if you swap I and j, that should be the same. So that means this is equal to, you swap I and j, so alpha delta ji delta kl plus beta delta jk delta il plus gamma delta jl delta ik. Now delta ij and delta ji are the same, it is a symmetric tensor. So what it follows, that if these two are equal, then what it follows? Beta is equal to gamma, right. So we have brought down the number of constants to two constants now, alpha, beta, and gamma is also same as beta. So alpha and beta. Now let us write an expression for tau ij. Tau ij deviatoric that is Cij into Ekl. So, tau ij deviatoric is equal toCijkl into Ekl, that is equal to alpha delta ij delta kl plus beta delta ik delta jl plus gamma is also equal to beta. So, plus beta delta il delta jk, this multiplied by Ekl. Now, let us simplify this. Remember that I j, these are sort of indices which are there appearing in the left hand side. So, we are not able to manipulate with that, because I j are already there in the left hand side. So, kl, these are sort of indices with which we can manipulate. So, delta kl, when is it 1? It is 1 only when L is equal to k. So, when L is equal to k, this becomes what? Ekk. So, alpha into Ekk, right, that is the first term. Second term, I and j we cannot disturb. So, Ekl, now you see delta Ik will become 1 when k is equal to I, and delta jl will become 1 when L is equal to j. So, this will become Eij, k will become I and L will become j. So, beta into Eij plus beta, now you tell what should be this, L is equal to I. So, and k equal to j, so Eji, so plus beta Eji. So, what is Eij? You recall we defined it in the previous lecture, half del uy del xj plus del uj del xi, and this is same as Eji, right. So, alpha Ekk plus, this is basically 2 beta Eij. So, beta del uy del xj plus del uj del xi. What is Ekk? Ekk is E11 plus E22 plus E33. This is what? Del u1 del x1 plus del u2 del x2 plus del u3 del x3. This is nothing but the divergence of the velocity vector v. So, this in the shorthand index notation you can write del uk del xk, right. So, EKK is del uk del xk. So, we can relate the deviatoric stress with a term which is the first term and which is a term which is the second term. Now, how do they relate with the physics of flow, that we should understand carefully. Now, the first thing that you must appreciate that this as well as these are kinematic parameters, right. These are pure kinematic parameters. Now, what do these parameters represent? The first kinematic parameter, that is del uk del xk, this represents the volumetric strain within the fluid. So, what is the rate of change of volume per unit volume of the, if there is a fluid element, then what is the rate of change of volume of that fluid element per unit volume? That volumetric strain rate is represented by this. So, if there is a fluid element that does not change its volume, then such a flow is called as incompressible flow. So, this term is 0 for incompressible flow. Remember, incompressible flow is a pure kinematic consideration. There is a distinction between incompressible flow and incompressible fluid. So, that must be understood very carefully. Incompressible fluid is a fluid where the density is weakly sensitive to pressure, the density is not changing with pressure substantially. So, the change in density due to change in pressure can be neglected, and it can be shown that like for Mach number typically less than about 0.3, that is the reality. So, that is the definition of an incompressible fluid. On the other hand, the concept of incompressible flow is a pure kinematic concept, and that follows from the consideration that if a fluid is not suffering from any volumetric strain, then the flow can be considered as incompressible. So, this is incompressible flow, should not be confused with incompressible fluid. So, this relates to the compressibility of the flow or the volumetric dilation, volumetric change within the flow, and this relates to what? This relates to the deformation, linear or angular. If I is equal to j, this is linear deformation, and if I is not equal to j, that is shear deformation or angular deformation. So, this is related to volumetric deformation, this is related to linear or angular deformation. So, then these constants have special meaning physically. So, what is this constant? This is nothing but the viscosity of the fluid, because this is the rate of deformation, and the deviatoric component of the stress, one part of that is linearly proportional to the rate of deformation, and that proportionality constant is known as the viscosity of the fluid. That is what is Newton's law of viscosity. Okay. But you know, this we have arrived at by considering a special scenario, a homogeneous isotropic fluid. So, that is why this is still not the most generalized form of the Newton's law of viscosity, but it is generalized enough considering the homogeneity and isotropy of the fluid. And this is a